All right, we'll go ahead and get started. There might be some folks trickling in the back, but that's okay. So my name is Stannard. I'm the founder and CEO of a company called Petabridge. We build open source tools for .NET developers to help build a highly available distributed systems. The biggest thing we work on is a technology called Akka.NET. I'm one of the co-founders of that open source project. It's a distributed actor model framework for doing sort of high performance real-time computing. So that's what I spend most of my time doing. Lately, however, because we're in the business of helping our customers build distributed systems, that also means we have to also be in the business of helping them figure out how to manage and monitor those distributed systems as well. And that's what we're going to talk about today, using a technology called distributed tracing, which is a relatively new tool in the application performance monitoring space. So I'm going to introduce this tool today. Apparently, I forgot to plug in my clicker for my thing here. All right, there we go. All right, so the first thing we're going to talk about actually is microservices and distributed architectures. There's been a number of workshops and other talks today about how to build these, some of the best practices for doing it, and so forth. I'm going to go ahead and address some of the problems that microservices introduce, and specifically their people problems. Microservices are great for a large number of reasons, but they do trade one set of problems for another set of problems. Distributed tracing is aimed at solving some of the problems that microservices introduce into your architecture. And so we're going to go ahead and cover what distributed tracing is in concept and how it works in practice. Then we're going to introduce some specific technologies. The most important one is called OpenTracing, which is a standard that is designed to be vendor neutral, meaning lots of different tracing products like Microsoft Azure Application Insights, for instance, or Zipkin or Jaeger. These are all names of different sort of tracing engines that you might use at your company. They all target this standard, which means that you can have apples to apples comparisons for people who are building frameworks like Akka.NET or ASP.NET MVC, where I can support all those different tools simultaneously by targeting this standard. That's what that's about. And then we're going to talk about some distributed tracing best practices. And I'm going to introduce a little demo using Jaeger, which is one of the open source tracing tools that's publicly available. Well, actually, before I keep going, quick show of hands so far, just so I get a feel for who's in the room today. Who in the room would consider themselves to be a back-end software developer? Quick show of hands. Okay, it looks like the lion's share of everyone in the room. Okay. Next show of hands. Who is currently working on a distributed architecture, whether it's microservices or SOA or whatever? Quick show of hands. All right, a lot of the same ones. Who is already using a distributed tracing engine? All right, there we go. Good. So we've got a couple of people who are already on board, and most of us are not. So last question I have before I jump in. Who is this your first time being exposed to distributed tracing at all, other than hearing someone mention it in passing maybe once or twice before? Quick show of hands. Okay, great. Okay, cool. That's helpful for me. Gives you the opportunity to modulate my examples and everything. So the old way of developing software, this has been sort of the standard architecture that most enterprise applications have used for the better part of 3 decades. It's all pretty recognizable. We have a monolithic application written in, typically, a single runtime, a single programming language, and a single code base, usually. That application, more often than not, has been stateless, and all of the actual sort of source of truth states usually been stored inside some sort of database, right? Well, the new model that we're working towards is a distributed architecture, microservices. Now, the predominant reason why we move towards microservices fundamentally isn't technical. It's actually about being able to scale the teams that build software, not the software products themselves. I can go ahead and take a really complex product and break it up into lots of distinct services, which can be developed and maintained by independent teams that program against essentially like network contracts, things like REST APIs, for instance, or using common messaging formats with tools like Kafka or Service Bus or Event Hubs, those sorts of things. So one of the big differences between how this system worked and this system worked is all of the programmers were working inside one process in a monolith before, using the same set of tools, and everyone typically had access to the same code base. So even though monoliths were sort of difficult and awkward to deploy, because you had to deploy basically if you changed anything, you had to change everything all at once, which made deployments rather inflexible and infrequent, I might add. At least all the developers on this team knew everything about how the system was built, and they could, if they needed to learn something, they could dig through the code. On top of that, we had the ability to tell a story about what happened when we processed an end user's request. We had the ability to tell that story using tracing tools like IntelliTrace and so forth, because all that information could be captured from the local context of a single process. As we're about to see with microservices, that breaks down once we start introducing different services, network boundaries, different runtimes, different frameworks, different programming languages, and most importantly, different people. So microservices are fundamentally a way of scaling software development teams, is how I look at it. Now, that being said, a lot of the work I do with Petabridge's customers is being able to introduce things like partial failure tolerance, using network boundaries to go ahead and physically isolate different parts of your system that have different consistency and availability settings and so forth. So there are some big technical benefits to microservices too. But the primary benefit behind them is it improves the agility of our software development organizations. If I take my product and I break it up into, let's say, 3 discrete services that all interact with each other using explicit contracts that were agreed upon sort of when they first built it. Well, I can have one team, let's say service 1 is the customer-facing part. So that's sort of like the web front end of your application. Well, I might have a couple developers, a front end, back end, an architect who kind of oversees the organization of all of it, and then some QA folks. On service 2, which is kind of more like business rules and middleware, maybe it does some fan out to some third-party services you use or whatever. You might have a slightly different looking team. And then the third team, where you might have a much more data-intensive microservice, where you're actually working with your database, working with your BI and analytic systems and so forth. You might have a DBA and some other types of people who work on here. And then lastly, maybe you have a shared infrastructure team that basically provides standards for how all these teams do deployments. They might be responsible for doing things like providing a standard way of deploying onto Kubernetes or Azure or Amazon or whatever your preferred runtime environment is. So what's really cool about microservices is service 1 and service 2 can potentially be implemented with totally different technologies. Pick the right tools for the job, right? And so you might have these sort of polyglot teams, or maybe team 1 is programming using React and doing a primarily JavaScript front end. Team 2 might be doing a whole bunch of work in something like Go or maybe Scala. And then team 3, if they're doing a lot of data-intensive stuff, maybe they're using .NET Core and are doing some work using sort of traditional, I don't know, OLAP type stuff. It could be whatever story you want to tell here. So that's great. We can pick the best tools for the job, and we can go ahead and hire the right people who know how to use those tools and integrate everything together through the magic of sort of network message formats and serialization. Well, while this makes it possible for us to use the right tool for the job, makes it possible for us to deploy changes to each one of these services independently, and allows them to go ahead and sort of manage their applications on their own release cadences and so forth. This type of organizational structure introduces a whole new class of problems we didn't have before in the monolith world. Probably the biggest problem, and this problem gets worse the more microservices you have and the more people you have, is loss of coherence. What exactly happens when my front-end service receives a request from an end user? Tell me the complete story end-to-end about everything all of our software did to serve that final result we send back to the end user. In a big microservices architecture, it's very unlikely there's one person who can answer that question. Because that knowledge around how each service works and how it's implemented and how it's using the underlying tools, now that's all decentralized amongst these programming teams that have their own expertise and tool sets. All right, so that's tricky. And it gets worse the more services you have. If you're like Uber, which is one of the companies that developed one of the open source one of the open source distributed tracing engines we're going to look at, They had something like 1,200 services that are all how to talk to each other to fulfill their application. You can't, no matter how smart you are, you can't have one person who can fit that complete picture into memory at any given time. Just beyond our capabilities, right? So that's an issue. Second issue is this loss of coherence makes distributed systems much more difficult to debug than a traditional monolith. If an exception gets thrown somewhere inside my monolithic application, I have the entire stack trace of everything that happened prior sitting there inside that process. And I can go ahead and attach a debugger to it and see what exactly happened. Well, now that errors can happen in a downstream service that I didn't program in a language I don't understand, using tools I've never heard of before, but someone else on my team, or someone else on another team does, what am I supposed to do as the developer on the upstream service that has to deal with the angry customer whose request didn't get processed on time? That's a problem. The other thing that makes this especially fun is that if you have to work with multiple sort of downstream services in parallel, your request can actually fail in multiple places in your system concurrently. So I might have failures in 4 different places all at the same time. And on top of that, the detail you need to debug those exceptions probably doesn't get propagated back in a very easily understandable or coherent manner. So that's another issue that makes this problematic for us. And then the last bit, the hardest part of software development is always the people. Being able to troubleshoot issues that occur inside a big distributed system now requires a much more precise level of communication between people on different teams than it used to in monolith land, where everyone had access to the same code base. It was all written on the same tools that everybody understood. Now that's no longer the case. And if you don't have, let's say, common infrastructure and standards, that's why we have a shared infrastructure team on that previous diagram. They're the folks who help us define those standards for how we do some things. If you don't have common standards, the phrases and words that Team 1 uses might be totally different than the ones that Team 2 uses to describe the same thing. So you end up with this sort of translation problem from there. I know it sounds like something out of a Dilbert cartoon, but it does happen. But most importantly, what you end up with are information silos. And so all of these problems essentially contribute to, ironically enough, making it more difficult for us to turn around fixes. The whole point of microservices is to be more agile and to be able to deploy changes and iterate much more quickly on our products. But this loss of coherence and the increased debugging time make it much more expensive for us to do that. The way historically people have had to go and debug sort of microservice issues, and I've been in the room several times having to do this, is you have an engineer from each team, from each service, pulling together log files and trying to correlate them all across all the different services. And I'm sure there's some vendors, some companies like Splunk that'd be very happy to sell you a 6-figure solution to help make that easier. And all I found it does is it actually just makes the arguments more intense when things occurs. So long story short, the way the tools that we have for trying to debug these types of problems out of the box don't scale very well. They don't scale as well as the actual sort of microservice architecture style is supposed to. So what do we need? What we fundamentally need is to take a tooling approach that worked really well inside a single monolithic process, and we need to go ahead and reorganize how we use it so it can now work across multiple processes that are written in different languages and use different frameworks and runtimes potentially. And this is what distributed tracing is designed to do. So a tool like IntelliTrace or some of our sort of single process tracing tools, we're able to go and give us a detailed stack trace and essentially tell the story of what happened from the perspective of a single process. It's fundamentally how they worked. Well, that breaks down as soon as you have process boundaries. That's the problem that microservices really introduces here. So distributed tracing is about, let's, in parallel, gather the story from each one of the processes that was involved in serving this request, and let's go and correlate and stitch those together so we can follow them as sort of a chronological timeline of when things happened. And that can include, by the way, things happening at the same time in different parts of your network. And that's what distributed tracing as a tool class is designed to do. Now, what I'm showing you right now, this is the user interface for Zipkin, an open source distributed tracing tool that was originally developed by Twitter in-house. So what you can see here, the font's probably a little small for the folks in back, so I apologize. What you can see here is I have a request that took about 48 milliseconds, and you can see that it has 8 spans. I'm going to go ahead and define what this term means in a little bit more detail in a moment, but you can think of a span as one logical synchronous operation that happened inside one of your processes, right? So if I have an MVC controller that receives one HTTP request, that might be my first span. If that controller makes an asynchronous request down to, let's say, Entity Framework or your database driver to go ahead and do a query, that's a second span occurring inside the same process. So this is designed to go ahead and allow us to sort of asynchronously trace things a little bit more easily. That's the big idea. And what I can see is that this particular request actually bridged 2 different nodes inside my network, 2 different instances of a service were talking to each other here. And I'm going to show you a demo in a minute where we're going to have a big sort of peer-to-peer Akka.NET network, essentially shouting data across all the nodes at the same time and then gathering it back, which is going to be a lot noisier looking than this. But that's just to show you sort of how complex, how even the most complicated requests can be captured using a distributed tracing engine. That's the big idea. Where this technology originally came from is it's only kind of been 4 or 5 years or so since this kind of entered the sort of consciousness of the software development community. This is all originally derived from a white paper that Google published around that time, 4 or 5 years ago, called Dapper was the name of it, which is their internal tool they use for keeping track of their requests inside Google's products. Since they published that paper, companies like Twitter and Uber and others ended up going and building their own tools that basically follow a similar approach. So that's what we're going to be talking about today. So the biggest feature of distributed tracing is the fact that all of those requests can be correlated automatically across the different services inside your network. So we have a way of essentially preserving what's known as the trace context. And I'm going to break down the different component parts of that. It's essentially 3 identifiers is what your trace context is. The trace ID, which basically is like one logical request inside your system. The span ID, which is the ID of a single local operation that's happening. And then the parent ID, which is, if I'm span number 2, span number 1 is my parent because that's who called me. So this is what allows us to go and correlate all the activity together. And I'll make that a little bit more obvious later. The next bit of distributed tracing is that every single span has the ability to capture really detailed information about the local execution context of that request. So I can append things like logs that were being recorded in real time. I can go ahead and record tags and metadata. So for instance, one really useful tag you might want to include in a span is, let's suppose you have a customer-facing e-commerce website where all of the customers have to log in with their account and put things in their shopping cart. Pretty standard. I can go ahead and include as a tag that user-specific customer ID. And that'll allow me to pull up the Jaeger or Zipkin dashboard, and I can search for all traced requests for that specific person if I want. So that's a really useful way of using tags to go ahead and make your data a little bit more, making your trace data a little bit more sort of semantically visible and everything else. The next really big feature of distributed tracing is that all of the reporting happens out of band. Meaning, if I have a big microservice architecture, I might have some spans finishing before others because this is all asynchronous. It's happening over the network, right? Well, a tool like Zipkin will be able to go ahead and grab those spans as they're being reported, and it'll be able to go and stitch together that timeline incrementally as that data comes in. So I don't need to worry about the ordering in which things finish. The tracing engine can go ahead and still build that story for me as it gets that data. So that's what the out-of-band reporting helps us do. We don't have to worry about when things get reported to the tracing engine. And lastly, the tracing engines themselves typically ship with, and this is actually sort of like one of the things that you're going to want to think about if you end up picking a distributed tracing tool, is what does this part look like? They'll go ahead and offer you some really good visualization and diagnostic tools for doing things like searching for specific types of trace data, or being able to go ahead and correlate different types of sort of similar looking requests together. It's like one of the things that Zipkin and Jaeger can do by default is they can show you what were your highest latency requests to this service over the past hour. So you can go and say, okay, why did this request run for, let's say, 1,200 milliseconds instead of the usual 120? What caused that order of magnitude increase? And what you might see in there is there might have been a SQL query that timed out and had to be retried, or something like that. So those are the types of things that a tracing engine can help call out and help explain to you. So these are the features of distributed tracing in general, as sort of a tool class. Now, in the real world, here is what building that trace might actually look like from the point of view of the instrumentation running inside your applications. How do we actually upload data to Zipkin? Well, here's what might happen. I have service 1 who receives requests directly from an end user running a web browser. Service 1 is going to go ahead and send a downstream request to service 2, and service 2 might do some other work under the covers that service 1 doesn't really have a lot of visibility into by default. And service number 3 is going to be doing a little bit more data-intensive stuff. Might be retrieving some data from SQL Server or Mongo or whatever. And we're going to go ahead and use that data to complete service 2 and service 1's requests upstream, right? So what's going to happen is the first span that might get reported to Zipkin might actually be the operation at the bottom of the call chain. That query to SQL Server might be the first operation that completes end-to-end. The next operation that might complete will be the HTTP call that caused that query to be executed in the first place. Essentially, this call chain is kind of unwinding itself as things finish, is what's going on. And you can see here, you notice the span counts are going down. So most span IDs in most of these systems are actually GUIDs, but for the sake of making it easy to sort of describe, you can see the span count is going up. This means that operation is essentially starting later in the process. And then we see span number 2 completes. So once service number 3 sends its results back to service number 2, service 2 finishes its work, then delivers its results to service number 1. And then service 1 serves its final result to your customer, to the end user who's browsing your app, right? So this is all the data making it to Zipkin. Through the magic of other people's software, Zipkin turns all that information into a trace that looks like this, where I can see that my end-to-end request time was 210 milliseconds. That's how long between request number 1 started and request number 2 finished. So that's all recorded in one span. And I can see that it took us, maybe 20 milliseconds or so to go ahead and trigger service 2 to start. Service number 3 started pretty quickly. And our database query only took about 40 milliseconds. And one thing I could spot as an engineer taking a look at this diagram, if I'm trying to improve our end-to-end response times, if that's something I'm concerned about, I could say, you know what? The fact that service number 3's MVC controller took an additional 100 milliseconds to run on top of the actual work the database was performing, that tells me there's probably a problem right here, that I'm doing something inefficient. Maybe my result set I'm getting from SQL Server is too big, and I'm having to go and do a lot of filtering on it. Or maybe I'm trying to serialize it into some format that's really expensive. Whatever the case may be, this kind of tells me where my performance bottleneck for most of the system is. Make sense so far? Good. So this is the idea in terms of what sort of output you can expect from a distributed tracing system. Now here's the benefits in doing this. Well, benefit in doing this is if I'm a developer on service 1 and I want to figure out why was my request slow, I now figure out it's the developers on team 3 who are wrong. And those are the ones who should get yelled at, not me. And I'm actually not totally kidding either. Part of the idea behind this is to give all the developers on all the teams that all work together cooperatively to serve your customers visibility into what everyone else is doing. Essentially, we can tell a story from the point of view of everybody who's working together on the distributed tracing system at the same time. Now, one thing I didn't mention about this, I guess when I was showing this diagram exactly, but potentially all of these different services can be implemented using totally different tech stacks if we wanted to. Like this could be React, this could be Scala, this could be C#. And all that data could still be understood inside Zipkin. The reason for that is the formats we use for propagating requests between each node are standardized as a result of the OpenTracing standard, which is what we're going to talk about next. after I go through this. In terms of distributed tracing tools, there's at least a dozen out there. It might be 24 now. So there's a lot of new entrants into this space all the time. So some of the open source ones, Zipkin and Jaeger. I'm going to be demoing Jaeger in a little bit, mostly because I think its user interface is more pretty. Therefore, it's going to show up better in the YouTube video and everything else. But on top of that, there's some proprietary solutions like Datadog, Dynatrace, App Dynamics, Application Insights, Google Stack Driver. I'm sure Amazon has one too, but there's tons of tools out there. Now, one small problem this introduces, though, is if there's all these different tools for doing distributed tracing, you don't want to be in a position as, let's say, a CIO or a tech director, where you have to say, wow, I guess we need to go ahead and find one distributed tracing tool that's guaranteed to work consistently across every possible tool combination we have. That'd be a bit of a daunting task. Hence where OpenTracing comes into the picture. So I work as sort of a library developer primarily. My job is to basically build open source tools for the benefit of people who do application development. So that's sort of what my clients are. Well, one of the things I have to worry about is I want to make sure my clients can go ahead and trace their applications with whatever tool their company picks. If you want to use Application Insights or you want to use Jaeger or Zipkin, I shouldn't have to go ahead and marry my framework to one of those tools. I should go ahead and be able to give choice back to the end users. That's primarily what OpenTracing is designed to do. We basically provide some tooling that is vendor neutral. And all of these distributed tracing tools, like Zipkin and Jaeger, target this standard and use the lexicon and some of the formats that OpenTracing standardizes. So I can go ahead and include OpenTracing bindings to something like ASP.NET Core middleware, or Akka.NET middleware, or to RabbitMQ if I want, something like that. And all of your driver code you use to report data back to Zipkin can be programmed against that API. Therefore, you don't have to necessarily worry about whether or not there's a Zipkin binding for ASP.NET Core. As long as there's an OpenTracing one, and there's a piece of middleware that does support it, you're good to go. And you can go ahead and bring whatever tool you want. But the most important thing the OpenTracing standard does is this bottom bit down there. The magic to making distributed tracing work is the ability to correlate which request triggered which. So we can go ahead and stitch them all together on that graph at the end. And that's what we call the propagation format, is what this is. Well, I guess I need to define some terms real quick. So the first term is a trace. So a single trace represents one end-to-end request in your entire system. If one end user request ends up spawning, let's say, 100 calls to different microservices, each one of those calls will be part of the same trace, right? So it's everything that correlates back to something we're delivering to an end user. That's a trace. And a trace consists of multiple spans. A trace consists of multiple spans. So a span can be produced by multiple distributed services, potentially. So spans can be produced by any part of your system. And a span itself is a single logical unit of work, essentially. So like one asynchronous method, if you're using the TPL in C#, that would be a span, potentially. And spans can have parents and children and siblings. So sibling spans run concurrently. They're running in parallel in two different places inside your network somewhere. A child span usually always starts after its parent started. That's sort of the relationship between them, temporally. The span context is where all that correlation data goes. So this is basically what defines the trace ID, the parent ID, and the span ID. And this is the thing that the OpenTracing standard helps us sort of robustly define in a way that can be communicated across process boundaries and across different runtimes and frameworks. And then we have the tracer. The tracer is the driver that you use to actually report data back to something like Zipkin or Jaeger. That's fundamentally what it is. So Petabridge, my company, we developed a high-performance Zipkin tracing engine for some of our users. And this is what it looks like from a code perspective. The iTracer interface is part of the Open Standard DLL that you can install as a NuGet package. So that's sort of the standard that like a tool like the OpenTracing middleware for ASP.NET Core would basically be programmed against that interface. And my specific implementation of that comes from my petabridge.tracing.zipkin NuGet package. And so I go ahead and spin up a Zipkin tracer, and I pass in this little HTTP URL right here. And what's going to happen is every time I go and build a span like this, well, I'm passing in the name of the operation I'm going to execute. So the name of your operation in like a web application might be the name of the web method you're using. So it might be, /API/items post or something like that. Might be the name of your operation there. So this is what we're going to use to go ahead and identify what was happening inside our system. And then I could pass in some tags, some metadata I can go and use to search this. And then down here, if I have another active span, so basically let's say there was another operation that was already running at the time I started this span, I can go ahead and say, you know what? This span that I created right here is actually a child of that one. And that way those two will be correlated together now on the graph. And then when I start this span, I'm going to go ahead and finish it here. And when I call that .finish, it's essentially like calling dispose on an iDisposable object. It's essentially the same idea here. That's going to go ahead and cause this span to get reported asynchronously to the Zipkin server living at this URL. Does that make sense so far? All right, good. Now, from a network perspective here, in terms of how are we actually passing that span context data around, what I'd probably end up doing inside an HTTP system is I would add some additional headers to each of my requests I'm sending downstream. So this might be something you set up when you create your HTTP client. I'm going to pass in a header that describes the trace ID, the span ID, and the parent ID of the previous request. And so when I go and I receive that request downstream, I can go ahead and tag the next span I create as being a child of the one that was described in that header there. And in fact, there is a W3C standard to go ahead and build this tracing propagation directly into the HTTP spec pretty soon. There's a working group around that for the time being. And that's largely built around the header formats that Zipkin uses specifically. So that's something that you'll see coming soon. And it's also possible that tools like ASP.NET Core might automatically begin propagating that sort of data downstream in a future version. Kind of depends on where the standard goes. But there's a lot of work being done around this because this is such a common problem that so many developers have. So for instance, these are what the sort of current B3. B3 is the format that Zipkin uses for representing this data internally. Any tool could technically use it, but this is just what Zipkin standardized on. So these are the HTTP headers you would see if you went ahead and were sitting in the middle of one of Twitter's data centers, potentially, and intercepted one of their requests between microservices. You might see these headers go and appear in one of them there. And this would go ahead and describe, this is the name of this operation, this is the name of the operation that came before this one, and this is the current operation. And then this indicates if we're sampling data or not, basically. So right now, we're not sampling anything. So the best practices so far for essentially doing distributed tracing inside your applications, first is you want to go ahead and standardize on those carrier formats that I just showed on the previous screen. How are we going to go ahead and propagate information from one service to another? So if you're using predominantly HTTP services, the easiest way to do that is to define some custom headers. And that's also hence why the W3 standard is being developed. Now, if you need to use something like, let's say, Kafka, or you want to use Azure Service Bus or Akka.NET, what you'd want to do in that case is probably go and define a little header dictionary that's at the front of every one of your messages you put onto your message bus. And then the consumer that reads them downstream would look for those headers and use that to create a span using similar API calls to what I just did on screen. So that's what you'd want to do there. If you can use tracing at the infrastructure level, you should. So if you have the ability to, let's say, inject a tracer into the ASP.NET Core middleware, so you can go ahead and start capturing information before it gets handed off to your controller, that'd be really useful for grabbing things like the authentication state of the user, for instance. That's a really good practice to engage in. And make sure you have more context available by default in every single request. That's a good practice. OpenTracing has a feature called a scope manager, which is really useful. This is a way of automatically figuring out what's the span that came before this one. So for instance, in C# and .NET, we have a scope manager that uses the async local context for doing async await and so forth. We can basically figure out what was the span that came before us in that call chain automatically. So that'd be an example of a scope manager implementation. And then the last bit, if you can have your logging infrastructure automatically, at the time you write a log, if you can automatically append that to a span, whatever the current span is, that's a good practice too. Essentially what we're doing is we're trying to put as much information into those contexts as possible. So when someone needs to go through and debug a request that failed or timed out, they have all that information from all the other processes involved in the food chain along the way. We want to have as much context as possible, in other words. So on that note, I'm going to go ahead and show a little bit of code and get into a little bit more detail on some of the instrumentation. And we'll take a look at the Jaeger UI and a brief demo as well. So let's do that. Then I'll have plenty of time for questions after that. All right. Grab that here. All right. So I think I'll start with a really simple example, actually. So we're going to be using Jaeger here. And we're using Akka.NET, which is a subject for a different talk at some point in the future. But all you need to know is actors in Akka.NET work by passing messages to each other. And so I'm basically recording a span every time an actor receives a message. That's basically how this demo is going to work. And if I scroll down here, actually, you know what? I guess I'll show this sample instead. We'll do the complicated one. Why not, right? All right, here we go. What's going to happen here when I spin this up is I'm basically creating a 4-process cluster of Akka.NET nodes that are basically all randomly screaming at each other. We're doing that intentionally to create a noisy-looking trace is what we're doing. So yeah, there you go. So all these nodes in the cluster are all trying to send pings back and forth to each other. Looks like they're slowing down a little bit now. There we go. All right. So we get the idea. Since I'm using Docker for Windows and I'm concerned about running out of memory on that tiny little Hyper-V VM, I'm going to pull the plug here. And then I can pull up the Jaeger user interface. So the first thing I can look at inside a tool like Jaeger, let me blow this up a little bit just to make it easier to read. Whoa. Not what I meant to do. All right, there we go. What I can do in a tool like Jaeger, and of course now I can't read that. What I can do in a tool like Jaeger is I can go ahead and see all the different services that are participating by their address inside my network here. So if you have, let's say, 100 web servers, you would have a list of 100 potential services here, even if they're running different services potentially. So I can say, okay, I want to take a look at all the requests that pass through localhost 2551. And I want to go ahead and see if there was any request that had a duration, let's say, minimum duration of 125 milliseconds. Oh, whoops, I guess I got to do MS. No results. That's good. Guess my system's nice and fast. Either that or no, looks like my system's just fast. Well, how about that? I'll take it. So I'm going to dig in here into this trace. I'm going to go and collapse everything down real quick. So this is the first operation that kind of starts my system off here. It's this little pinger actor. This actor basically runs on a clock and sends a message to itself that it's going to end up broadcasting to other nodes in the cluster. That's fundamentally how it works. What I'm going to do here is I can go ahead and see that I recorded a log event inside this trace that basically just shows me here's the C# name of the message I received. Generate ping is the name of it. And I can go ahead and see some of my tags. I can see that this is the actor. I can see what the message type was. And I can go ahead and see who the sender of this message was. If I open up my graph, I can go ahead and see that this message then made it to the /user/random actor. This is another span inside my system. And if I go ahead and take a look here, I see I've got a couple logs this time. What's that data look like? And I can go ahead and see down here that some of the default Akka.NET logs were captured automatically. So this little info message and everything else is a log that I'd normally just write out to the console or to Elastic or something like that. So I'm actually appending that to this trace. Then here's where things get kind of fun. I went ahead and from this node, localhost 2551, I went ahead and I broadcast a copy of this message. Let me stretch that out a bit. I broadcast a copy of this message in parallel to localhost 33720, so another node running inside the same network. And I also broadcast it to localhost 2552 at the same time. So one node broadcast a copy of this message to two other nodes. So now I have two traces running in parallel for the same message. And if I keep going down this rabbit hole here, because this graph is intentionally noisy, we wrote this to stress test the driver that we built. So that's kind of what it's for. I can go ahead and follow this all the way down to its logical conclusion. So this helps me do, for instance, if I want to go ahead and see if there was an undeliverable message somewhere inside this, this application, I could go ahead and search, if I wanted to. Let's see. Let me take a step back here. I can go ahead and search for, pull that up. Well, it's not giving me the option to do that there. Oh, here we go. System / okay, it looks like I already found one. Good. This actor right here, you may not be able to see it. It's called /system/dead letters. It means there was an undeliverable message somewhere inside my system. So this is like an error path, essentially. If I go and click into here, and I take a look at the sender, I take a look at the logs, I can see that this message was sent to an actor at location fake actor inside my system. I can reasonably assume that the programmer who worked on that probably screwed that up. Just inferring from the details there. But if I really wanted to go ahead and get a story from one of my other developers about why did this request time out, looking for a dead lettered message would be one of the symptoms I'd go and check for. If a message made it into dead letters, it means nobody processed it. Therefore, that would probably be something that would cause a timeout further upstream. I can go dig into the details that a tracing tool like Jaeger gives me to help figure that out in a matter of minutes. We had one user, major financial customer, who basically had spent weeks trying to debug a big Akka.NET cluster. And their issue was that after a certain period of time, requests started timing out more and more often inside their system. And they couldn't figure out why. Well, it turns out they were locking up a bunch of actors with a really expensive sort of bit of math that they were doing. And as they kept sending more requests, those requests started stacking up, and the actor couldn't respond within a certain timeout window. So they were able to use that data, whether they got within a matter of, let's say a couple hours of using a tracing tool like this, and figure out they needed to restructure their actors rather than trying to change timeout settings everywhere. Because the problem was architectural. It wasn't a configuration issue, in other words. So these are the types of things that distributed tracing can make less expensive, is they give you a complete story from the perspective of every part in your system that participated on what happened and when did it happen in the processing chain. Make sense? Good. Now just a little bit of code before I take some questions. Let's see. Alt-Shift enter here. All right. So just a little bit of code in terms of some of the OpenTracing instrumentation. If I go ahead and I scroll down here, I'm going to highlight this. Actually, let me zoom in, since I think Visual Studio will let me do this without breaking text wrapping, any of that fun stuff. All right, here we go. So here's an example here of being able to go and append log messages to the current span. I'm basically taking whatever the active span is, and I'm calling this .log method on it and just sending a string its way. That'll go ahead and take my formatted log message, and we'll go and automatically append that to the current operation in progress. Now, if I want to go ahead and log a sub operation, if I want, I can go ahead and do context.get instrumentation. This is an Akka.NET API, the instrumentation bit. Call the tracer, build span. We'll call it NDC op. And I can go ahead and say start as active. And I'll open up this using block. And I'll stick this in here. What this is going to do, this using block, is it's going to create a new child span that is a child of whatever the active span is. So this will show up underneath whatever the current span is on that histogram. And I can go ahead and add some log messages or tags or whatever to it. And then when I'm done, when that disposing block exits, that child span will be marked as complete. The amount of time it took between when that span started and stopped will be recorded on the histogram. And it'll be uploaded to Zipkin eventually. And that's where we go ahead and get these little performance metrics here. Like we can see this operation took, I guess it'd be 1/100th of a millisecond. So that's because this is all in-memory message processing for the most part. It's pretty fast. But that's some of the data you can go ahead and get from this. And this will help build a sort of a picture of what the end-to-end processing time took as well. Now, the last thing I should mention about some of the features of the distributed tracing tools you might look at, overwhelmingly, all of them support some form of sampling. Because as you are probably getting a sort of an idea of now, some of this information can be quite verbose and quite text-heavy. Therefore, in a really busy production system, you don't want to go ahead and slam all of your infrastructure with lots of logs and text being sent over the network everywhere. Therefore, tools like Jaeger, Zipkin, and even the off-the-shelf commercial ones all support some form of being able to say, only give me like 1% of all requests, or only give me requests that start with this HTTP verb or something else. So you have the ability to kind of constrain how much information actually gets produced by your tracing tools. So that being said, I'll eventually figure out how to pull up PowerPoint again here. There we go. That'll go ahead and do it for our presentation today. If you're interested in learning more about distributed tracing, here are some resources you can look up. You can go to the OpenTracing project. They have some good information on their site. You can also check out Zipkin, and you can take a look at some of their projects on GitHub. And if you have any questions about OpenTracing or distributed tracing in general, I think I have a few more minutes before the official lunch break starts. So I'd be more than happy to take any questions you might have. But otherwise, thank you very much for attending. Okay, any questions? Yes?
In the Jaeger UI set, can you filter query on any of that data that it traces?
Yeah. I should be able to go and filter, let's see. So I can go ahead and do it by the tag right here. So let me try actor.receive.sender equals system dead letters. Let me give that a try. I have to remember if I got my tag name right. But yeah, you can basically filter there by those sorts of things. Or session IDs, user IDs, that sort of thing. So like one really common use of tags that like a lot of our like production users will do is they'll tag the environment you're running inside of there. So it's like, is this if you're using Kubernetes, you might have like a live and a dark live. They want to go ahead and see like, oh, what did the dark live that's going to be running the next version of our code do for the same request? Yeah. So they'll use things like that for it. Yeah, each one of these tools has this little own query syntax for doing that inside this box here, and I'm less familiar with that than I am writing drivers for the things, but yeah. But yeah, you can go ahead and basically do like and or type stuff to search it. Yep. And I should also mention that the backing stores that some of these tracing tools use, Jaeger, for instance, has the ability to save all of its span data directly to Elastic if you wanted to go ahead and use more detailed queries on that if you wanted to. Yeah. Any other questions? Yes, in back. Yeah, basically it's one operation within one microservice.
Yeah. So when you're setting the header on the field, you're setting the parent span ID, and like
The current span ID is going to be the parent for the next operation downstream. Yeah. So yeah, it sort of it depends on basically how you want to use that propagation data, because technically it might be possible for a span to actually be like sent over the network and completed on the other side potentially. So using, like, let's say a queuing system like Rabbit, you might want to go ahead and start a span when the message gets flushed on one end, close that span when it gets processed on the other.
Does that mean that you then you open them via the API so that they're started?
Yeah. So basically, if I go ahead and pull up the OpenTracing stuff real fast, just to show you for completeness, if I got rid of this using block here, which is doing this for me automatically, so I'm going to delete that, and I guess I need a semicolon somewhere. So when I call, I think I have one extra parenthesis, there we go. So when I call start, that basically turns the timer on for the span. When I call down here, new span dot span dot finish, that basically completes the timer down there. So what I might do is I might go ahead and rehydrate this span on the other side of the network by doing, let's see, I'm just not going to bother formatting that. What I might go ahead and do is grab my tracer again. Tracer. Build span foo. I can say as child of. And I go ahead and pass in a span context there. So I guess actually technically I wouldn't be able to go ahead and start a span on one end and complete it on the other because that start time doesn't get propagated. So you would want to go ahead and have one span on one side for the start and another on the end for when you receive it. And that transit time in the middle will just be the delta between when if one operation ended and when another started. And you'd see that show up on the graph in Jaeger. Yeah, good question. Any others? Yeah.
We currently log to Elasticsearch and visualize with Kibana.
Mm-hmm.
So would it be just a case of changing that URL to push it straight to Elasticsearch for OpenTracing?
You know, there is probably, so I personally haven't looked at it, there's probably an OpenTracing instrumentation for Elasticsearch out there that'll just do all the correlation that you need in Kibana somewhere. So someone's probably got an adapter driver that does that for doing some of that correlation work already. So yeah. So if you already have dashboards and the thing that you're looking to get out of OpenTracing is, let's say, a more reliable way of correlating stuff together other than timestamps, sort of the schema that OpenTracing uses can be very helpful there. Make sense? Yeah.
What are some of the advantages of collecting this tracing data in the application code rather than using something like a sidecar pattern?
What are some of the advantages of collecting this data in the application code versus a sidecar pattern? So I'm actually, under the covers here, doing both. So I'm using the sidecar bit under the covers with a tool that our company developed that basically automatically captures information from the background. And that's kind of what I was mentioning earlier. If you can inject that tracing code directly into, let's say, your ASP.NET middleware, that's probably going to be much more useful than doing it directly in your line of business code, right? You don't want to necessarily clutter up your business logic with instrumentation code, right? That's going to be technical debt you might have to pay later in the future, right? The advantage of putting that instrumentation code right there is I can go ahead and grab contextual information that my infrastructure doesn't know about, for instance. So let's say if I have something that's very contextual, this customer doesn't have enough funds to go ahead and complete checkout, right? That's something that I probably am not going to be able to discern from ASP.NET. I might want to go ahead and have some way of passing that information into my tracing system. So if you can come up with a, let's say, a cross-cutting way of injecting the ability to capture that context into your infrastructure, you should. But in some cases, you might just have to bite the bullet and just call a log method on a span, right? It's kind of, you got to go ahead and pick what's going to be the most practical route for getting that done, even if it does introduce maybe a little bit of technical debt or looks ugly, whatever the case may be, right? Does that make sense? Yeah, you're welcome. Any other questions? Yeah, go ahead. Yeah. So your question, if I can go ahead and summarize it, is when you've got teams using different tools, like let's say not everybody's using Akka.net. Let's say we got one team using web services that are built in HTTP, and that service writes out to Kafka. And then you've got a bunch of folks using, I don't know, Scala agents sitting on the behind the scenes there. How do you make that work? What you want to standardize on is basically you can go ahead and use a driver that points to the same Zipkin instance, because there's basically implementations available in all these languages. The thing you want to standardize on is how do I inject the context from ASP.NET into that message going on to Kafka, and how do I read that context back out on the other side? And so that uses, there's a set of APIs I haven't really gotten into in the OpenTracing libraries. It's called the propagation APIs, which basically package that information from the current span and inject it into some sort of wire-friendly format that can be serialized and sent over the network. So you just want to standardize on where you do that. So like a good place to do it in that scenario I created would be on the Kafka subscriber and publisher code. You want to go ahead and have some way of grabbing the context from whoever published to me, inject that into maybe a little header in your Avro messages that go into Kafka, then have the consumer on the other side grab that same header and create a new child span. So that's sort of the general practice there. And that's also why I mentioned as a best practice on that previous slide, you might need to go and have some standards around how you do this within your organization in order for it to work. Any other questions? No? Well, thank you very much for your time. I really appreciate it. If you have any questions that you want to go and grab me when I'm out in the food area later, I'd be more than happy to answer them. And I hope you enjoy the rest of the conference. Thank you very much.